Okay, so now we have this question, which I will use to emphasize the concepts of normal contact force and frictional force, and specifically the nuances of it. So, it's a simple setup, right? We just have a mass that is on a slope, and there's friction between the mass and the slope. And that slope is the angle theta, and we're asking if the theta is increased, right? The angle is increased, how does it affect the normal contact force and the frictional force? So we seek to find expressions of the normal contact force as a function of theta and the frictional force as a function of theta, because having these expressions, right, having these functions, these analytic expressions would allow me to see as I increase theta or decrease theta, as I increase theta, sorry, how it affects these two functions. And so let's first seek to understand the normal contact force, right? So we'll talk about friction later. So for the time being, I'm turning off friction. And we can kind of do this because friction will only be parallel, will only affect the parallel components of the force. So and the normal contact force is perpendicular to it. So whether friction is on or off doesn't affect the magnitude of normal contact force. Right? If you didn't understand that, it's okay. Just know that I'm turning off friction right now so we can focus on the normal contact force. And we won't have any issues with it. Okay, so I'm gonna draw the gravitational force in blue, and I'm gonna draw the normal contact force in red. Okay, and I'm writing arrows on top to emphasize that they are vectors. So now the net force, right, acting on an object is the sum of the individual forces. So in this case, we have two forces, gravitational force and normal contact force. And what's the geometric intuition for summation of vectors? It is that you align the tail of one vector to the head of another. So if we draw a parallelogram, right, such that if we draw a parallelogram spanned by these two vectors, get something like that, and we get that F net, right, is the purple vector. I use purple because purple is red plus blue, right? So F net is the normal contact force, the red arrow, plus the blue arrow. Okay, so you may be wondering, hey, wait, didn't I make a mistake? Why did I draw F net such that it's sinking into the ground, right? And I did that to emphasize the fact that so far, I didn't know the magnitude of n, right? I didn't know the length of n. I drew it to some arbitrary length, and I purposely drew it short to show you that if I chose the wrong value of n, then the net force is into the ground. And why is net force into the ground bad? It's bad because net force into the ground, right? F net equals to ma, right? And if F net equals to ma, then that means that acceleration will have two components. One, acceleration vector, right, will be proportional to this purple vector, and there'll be one component that is perpendicular to the slope, and there'll be one component that is parallel to the slope. The parallel component is no issue, right? I have no issue with the mass accelerating parallel to the slope, right? It's just sliding up and down the slope. But I do have an issue with this. Right? If I have a perpendicular acceleration of the mass, then that implies that the mass is sinking into the slope, sinking into the ground. And remember, who doesn't like that, right? Remember that normal contact force hates that, right? Normal contact force will always adjust its value, right? It will always adjust its value such that the two objects do not sink into one another. So the reason why my F net is sinking into the ground is because the normal contact force is not large enough. So we can see that the normal contact force, I wanted to draw this diagram to emphasize the idea that the normal contact force will always do whatever it can to prevent sinking, right? And in this case, if the normal contact force initially is a small value, it realizes that, oh no, my object is sinking into the ground, right? What the normal contact force will do is it'll panic a little and it'll adjust itself, right? It'll adjust itself. Nature will adjust normal contact force such that it now has a larger magnitude, And now if we see the sum of the two vectors, right, with the larger magnitude, we see that the sum of the two vectors is now, right, this new f net. Right, this new f net is now parallel to the surface. So this diagram over here emphasizes that normal contact force will always adjust its value such that there's no sinking, right? Such that this A perpendicular, right, is equals to 0. Okay, so now that we have the idea of this tells us information, right? This tells us information about how to find the magnitude of the normal contact force, and that allows us to derive an expression n of theta. So how do we do it? Right, let me just go over here and draw a new diagram. So I have the box M, and it has mass M, so gravitational force mg, and n, and the normal contact force is perpendicular to the surface, right? So we want the sum of these two vectors to be purely parallel to the surface. So over here, remember I said previously that on the topic of vectors, right, every vector can be decomposed into a linear combination of the basis vectors. So if we chose the basis vectors in this case to be this one and this one, right, if we chose the basis vectors as such, I'll call them E parallel hat and E perpendicular hat. Right, so if I chose these basis vectors, then the mg vector, right, the mg vector, which I drew in blue just now, this mg vector can be decomposed into two component vectors, which I draw in dotted lines over here, right? And what are the corresponding magnitudes? One can perform angle chasing and find that this angle is theta. So the magnitude of this perpendicular component is mg cosine theta, and the magnitude of this parallel component is mg sine theta, right? So if I really wanted to be mathematically precise, I would say that the gravitational force is equals to mg cosine theta. This is the magnitude times um, times minus E perpendicular hat, right? Plus the magnitude mg sine theta times minus E parallel hat. The reason for these minus signs is because the E parallel and E perpendicular is pointing like towards the top right as positive, right, and towards the top left as positive. So if I want down right and down left, right, then the we must add a minus sign to flip the vectors. So this is minus E perpendicular and this is minus E parallel. Okay, so if I wanted to write in vector equation, this would be right. But for most of these questions, drawing a diagram and labeling their components like that would be enough information. Okay, so now we see that the sum, right? We said previously that the sum of these two vectors, the sum of the red plus the blue, must be purely parallel. So we basically want the sum of the red and blue to be purely parallel. And purely parallel means that f net must be equals to, right, must be proportional, right, must be something times E parallel, right? It must have a zero coefficient of the E perpendicular vector, right? It must have zero magnitude in the perpendicular direction. And we see that because we chose a good basis over here, now we see that the perpendicular component, right, because the normal contact force is just the magnitude of n, right? N is just the normal contact force is just n times perpendicular, the normal contact force only has a perpendicular component. So if we want the perpendicular components to vanish, we necessarily must have that mg cosine theta must equals to n. So that is our first relation for that's the now we've essentially found the normal contact force as a function of theta. Okay, so another way to see this is to see that the dotted line over here, the dotted line, the perpendicular components, the perpendicular forces, there's only two contributing vectors. One is this red vector, and one is this dotted blue vector. The magnitude of the red vector is n, and the magnitude of the dotted blue vector, right, this dotted blue vector is mg cosine theta. They're opposite in directions. So in order for them to cancel, the length of the red vector must equal the length of this dotted blue vector. So n must equals to mg cosine theta, right? And what's left over, right, would be mg sine theta in the parallel direction. And that would be useful for friction, but we'll come to that soon enough. Okay, so anyway, this is our first expression for normal contact force. And this is our expression for normal contact force, and let's do something similar to the frictional force. So, question now, right? Just now we turned off friction. Just now at the very start I said I turned off friction, but now we're going to turn it back on. So now friction is turned on. Turn on friction. Question, which direction is friction in? So if I have this same setup again, I have mg, and now we know that n, right, is equals to mg cosine theta, right? If I add these two vectors up, where would f net be? We saw that f net was in the parallel direction, downwards the slope. So if I didn't have friction, right, the object would slide down the slope. Very intuitive picture, object slide down the slope, right? Now if I do have friction, if I turn on friction, friction will always oppose sliding motion. In this case, the object is sliding down the slope. So friction will be in a direction that opposes sliding down. So in other words, friction will be between, right, the box and the slope, and it'll be pointing upwards the slope. So I'll call it F friction, right, and it's a vector. And with this, right, now there's three forces acting on object M, right? So F net must be equals to, there's now three forces acting on the mass, and friction will always adjust its value, right, to the best of its ability. It always adjusts its magnitude such that the acceleration, the sliding acceleration is 0. In other words, friction wants the parallel acceleration to equal to 0. So that means that if I sum up these three vectors, right, I put them tail to tail. So this is n, this is mg, and this is friction. Yeah, put them tail to tail, then I must have that they form a closed triangle, right? Because if they form a closed triangle, then that implies that the sum of these three vectors is the zero vector, right? With the zero vector has zero magnitude, zero length. So from this picture, actually I can see that because this angle is theta, right? Through some angle chasing, this angle is theta. You see that n, right? We got the previous result that m must be equals to mg cosine theta, because mg acts as the hypotenuse and this is the right angle. And the other result will just be that the frictional force must be mg sine theta. And so we found our answer, right? Frictional force as a function of theta, right? Just now I used f as a function of theta, just mg sine theta. And normal contact force we derived previously is mg cosine theta. And so now all that's left to do is to analyze that if I increase theta, right, how does friction and normal contact force change? So if to do so, just plot the trigonometric functions, right? We know theta is between 0 and 90 degrees. At this point in time, theta is between 0 and 90. So cosine theta looks like that, right? Cosine theta looks like that. And sine theta looks like that. So you can see that as theta increases, right, sine theta is increasing and cosine theta is decreasing. So the normal contact force is decreasing and frictional force is increasing. So the answer is D. Okay, so this is a very simple question, but I drew the diagram. I spent a bit more time talking about the normal contact force because I believe that this is a good opportunity to emphasize how normal contact force adjusts its magnitude, right, to prevent sinking into the ground, and likewise how friction adjusts its magnitude, right, to prevent sliding down, right. So friction will always want A parallel to equals to 0, and normal contact force will always want A perpendicular to equals to 0. Okay, at least in this context. So yeah, that's it for this question.